Hey everyone, and welcome to this explainer. Today we're putting on our master-level environmental engineering hats to unpack a really foundational text, Chapter 2 of the MENE 313 course manual. We're going to be looking at waste characterization and energy potential. And don't worry, we're focusing on the 20% of concepts that basically explain 80% of the entire chapter. Think of this as your ultimate blueprint for making super resilient waste-to-energy, or WTE, decisions. Let's get into it. So let's just jump right in with a massive question for you, my future colleagues. Why exactly do million-dollar waste-to-energy plants fail? Well, surprisingly, it's usually not because the core science of combustion or digestion is wrong. It's almost always because of the feedstock. You see, unknown waste isn't just trash. It is a massive financial and environmental risk that's just waiting to happen. And that brings us to this absolutely crucial quote from our source material. A waste stream may appear useful because it is abundant, but abundance alone does not make it suitable for energy recovery. This perfectly highlights the wrong way to design a plant, picking some shiny new technology first, versus the right way. The right way is letting the actual anatomy of the waste dictate the technology. Trying to do it backward, that is exactly how you end up with a stranded, useless asset. All right, here's our roadmap for today. We'll cover 1. The foundation of WE design, 2. Physical and chemical properties, 3. Biological traits and suitability, 4. The technology matching framework, 5. Exam critical takeaways, and finally, 6. 10 essential review points.
Jumping right into part 1, the foundation of WIT design. Look, WT infrastructure is incredibly expensive, and it's built to last for decades, right? So to protect that investment, we rely heavily on waste characterization. The text defines this as the systematic identification of waste quantity, composition, physical, chemical, and biological properties, and handling needs. Basically, this definition is the vital bridge that takes a messy, real-world waste problem and translates it into the hard data you need to drive a successful million-dollar engineering decision. Without it, honestly, you are just flying blind.
Moving right along to Section 2, Physical and Chemical Properties. Okay, so how do we actually measure this stuff? We use some very tangible metrics to evaluate waste as an engineering feedstock. 2 of the absolute most critical are heating value, which is simply the gross energy released by combustion, and moisture content, which is the water contained in the waste. Here's the kicker, though. High moisture is the ultimate enemy of direct thermal conversion. Think about it. Every single drop of water in that waste stream has to be heated and evaporated before you get any useful energy out of it, and that drastically lowers your useful heating value. Now, when we get the waste into the lab, we do 2 main types of chemical analysis. First is proximate analysis, which gives us moisture, volatile matter, fixed carbon, and ash. This basically shows us the macro behavior of the fuel. But then we have ultimate analysis, which breaks it down elementally: carbon, hydrogen, nitrogen, chlorine, and sulfur. Guys, this distinction is tested all the time. Why? Because ultimate analysis literally dictates your entire design for air pollution control. High chlorine or sulfur means you absolutely must design for acid gas neutralization and aggressive corrosion, or your plant simply won't survive. All right, let's pivot a bit to Section 3, Biological Traits and Suitability.
So now we're shifting our focus from burning waste to the specific properties that dictate if microorganisms can do the heavy lifting for us. And this perfectly illustrates the whole cause and effect relationship in waste engineering. Just look at how moisture behaves differently depending on the pathway. In a thermal mass burn incinerator, high moisture requires auxiliary fuel, demands drying, and tanks your efficiency. It completely ruins the process. But in biological WT, that exact same high moisture property is a gold mine. It actively supports microbial conversion and makes an anaerobic digester thrive. The waste itself hasn't changed at all. Our engineering context has. Here we're contrasting 2 prepared pathways based on traits. Biodegradability is an organic material's capacity to be decomposed biologically, which obviously points us toward digestion. On the flip side, we have refuse-derived fuel, or RDF, which is a prepared combustible fraction of waste, pointing us straight toward thermal use. This just really reinforces that we have to physically and biologically test waste to see if it's wet and degradable or dry and combustible, way before we even think about assigning it to a digester or a boiler.
Which brings us to Section 4, the technology matching framework. Okay, so how do we synthesize all this lab data into actual technology selection? Well, we walk through this matrix, and it takes real engineering judgment. If you've got mixed municipal solid waste, its composition is all over the place, meaning it requires sorting first. You can't just toss it in a reactor. Food and green waste? That's biodegradable, leading us to anaerobic digestion. Dry paper and plastics are highly combustible, making them great candidates for RDF or thermal routes, after recycling is considered, obviously. And sewage sludge has massive water content, which requires dewatering and a very pathway-specific analysis. You absolutely must screen these hierarchy options before committing to energy recovery.
And that leads us to the ultimate blueprint. It is a highly disciplined 6-step sequence designed to prevent incredibly costly mistakes. First up, classify the source. Second, screen your waste hierarchy options. What can we actually reduce or recycle here? Third, measure those critical properties like heating value and moisture. Fourth, estimate your real energy potential. Fifth, match the data to the right pathway. And finally, check your implementation conditions like supply stability. Following this stops you from forcing a waste stream into a pre-chosen technology it just doesn't belong in.
Let's hit Section 5, Exam Critical Takeaways.
All right, listen up, because we're going to synthesize this specifically for mastering your exams in your future design applications. I'm going to rapid fire these cause and effect points. First, energy potential is definitely not total mass. A ton of wet waste yields way less energy than a ton of dry waste. Second, chlorine and sulfur completely dictate your air pollution and corrosion design. Third, ash fusion temperature determines your risk of slagging. If that ash melts and sticks, your combustor is going to fail. And finally, taking a single grab sample of municipal waste is scientifically useless. Real sampling requires triplicates and compositing because municipal waste is just so massively variable.
And finally, Section 6, 10 Essential Review Points. Consider this your master's level cheat sheet. Let's run through them. 1. Technology choice always starts with the feedstock. 2. Apply the waste hierarchy before you even look at energy recovery. 3. High moisture destroys your thermal value. 4. Proximate analysis gives you macro burning behavior. 5. Ultimate analysis gives you elemental and emissions data. 6. Biodegradability points straight to biological digestion. 7. Chlorine and sulfur dictate your acid-gas controls. 8. Ash content drives your entire residue management system. 9. Refuse-derived fuel still requires intense consistency testing. And 10. Supply stability. Knowing for sure you have the right waste for the next 20 years dictates your financial viability. To wrap up this explainer, I really want to leave you with something to chew on. We've seen just how precise these characterizations have to be. But waste is a human product, right? It changes. If recycling rates suddenly soar, or product packaging shifts dramatically, and the composition of our waste changes tomorrow, will your facility actually survive? The real-world stakes of rigorous characterization and supply stability are absolutely massive. Thank you so much for joining me for this explainer, and keep asking those tough engineering questions.